Okay, let's continue to the next video sections. In this video sections, we will discuss this PointNet++, which is the further development of this PointNet. And these two papers are in the same years, 2017. If you open their papers, they are belongs to the same authors. It means that they belongs to the same research group. They just in the different conferences. Here we list the some of the issue that we already discussed in the previous video sections, and PointNet++ will address this first issue, which is the local features that are captured by PointNet are not strong enough. Okay, so let's start with the motivations of this PointNet++ work. For the 3D recognition, especially for the semantic segmentations, capturing the local informations are really important, as we can see that the PointNet only capture the point-wise local features. Let's review. For example, if we have this specific layer, the output of these point features, we have the number of point here. For example, we have 1000. This is the first point features having these embedding dimensions. This particular point features only consider this corresponding input single point by applying this MLP. And then again, the next point feature here only considers the corresponding input here by applying the same MLP. So that's why this kind of feature extractions are not enough. And this PointNet++ try to address this by capturing hierarchical local structure information, as we can see in this figure here. So the PointNet++, to extract a single point features, it consider the neighbors, as we can see here, the unit ball. And then instead of only capturing the single hierarchy, they call this set abstractions. We capture several hierarchies here. So later we will have three set abstractions that capture different hierarchies. Yeah, so this is the motivations of this work. And let's see the details of the architecture. Here we have several components of the architecture from this PointNet++. The first is this basic hierarchical point set feature learning that extract the different scale and different hierarchy. The first set abstractions and the second, and so on. And then the next we have these segmentations branch network here. And next we will have this is the corresponding classifications branch network. And we will discuss the detail one by one in the next few slides. Okay, so let's see the backbone, how they extract the point features that consider neighbors and also consider multiple hierarchies. First, second, they consider different hierarchies. So in each hierarchy, they have so-called SA layer or set abstraction layer. And each SA layer, they have these further layers. The first is sampling layer. Basically, it's just sample. We can see this dot here is the sampled layer as centroids. And then after we have this sampled points, we will do grouping. This point correspond to this point. And we consider these neighbors. And grouping layer basically just how we group this centroid and also its neighbors into single point feature here. So this is how we group this locality feature here. And then the next layer here, PointNet layer, is basically just fusing. After we group this centroid and neighbors, how we do fusing into single point vector. Let's say we have this every point feature here, and this is the embedding dimensions, the output of this number 3. Okay, let's discuss more details one by one. So in the sampling layer, they use FBS, farthest point sampling. For you who are not really familiar, let me give illustrations. So FBS, we can start with a random point. Let's say we sample in this point. And then in the next sampling, the next iterations, we consider the farthest point from the existing sampled point. Let's say the farthest is here. So in the next iteration, we sample this point. Again, the next iterations, we sample another farthest point from these two sampled points. Let's say the farthest is here. So this is the next iterations. And the fourth iterations, probably here, the farthest one. And next we will have something like here, and so on, here, 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 and so on, until we sample the number of points that we expect. And actually this figure is not really represent the FPS, but I think it's fine. It's just visualizations of their paper, probably just to simplify. Okay, so yeah, this is the sampling layer. Basically, we just sample. And in the original paper, they have the original of points are 2000 something. I forget the detail. And then later we sample into 500 something. Here, this is the FPS sampling. Okay, and then next we discuss this grouping layer. So this grouping layer, try to construct the local region set. If we have this centroid correspond to its sampled point here in the previous layer. And here we sampled Ni centroids. In the next few slides, I provide the exact numbers of every SA layer here, how many centroids we sample. Okay, and then for every centroid here, we consider the neighbors. We use the unit ball, the radius. For example, we can see here the ball using the certain radius, and we limit to only sample maximum k neighbors here. So this is the number of centroid, this is the number of neighbors. And then the D here is the original XYZ. And C here is the point features. For the first set abstractions, we don't have point features, so we can use like normal vectors, or we can use the point cloud colors if we have. And then for the next layers, for example, later if we process this, the C is C1 here. C1 is actually the output from the previous layer here. We fuse into this layer and later we use this one. But for the first SA layer, we just use this. The original point coordinates, or use the normal or use the color. Okay, so after we compute the k neighbors, and then the grouping layer is how we group this every centroid and its corresponding neighbors. And in this PointNet++, they directly compute the relative distance, which are the neighbor's point, subtracted by this centroid here. So the shape will be the same, because here we have the same number of n here, n centroid, and k is the neighbors. The center we have 1 here, right? This is the same, and this is the same. So if we subtract this to this, we will have this shape, right? Yeah, so this is the output of grouping layers. And then in the next layer, still in the same SA layer here, we have the PointNet. And in high level, PointNet will just fuse the grouping layer here into a single point features. So from the previous output, we have this relative distance. This relative distance is actually just subtracting the neighbor to the centroid. And then we apply PointNet. PointNet is basically just stack of MLP. So basically we just map this embedding dimensions into this new embedding dimensions. That's it. And we have this still same dimension here because we apply MLP only in this embedding dimension. So this is the PointNet layers. And then how this PointNet++ do the hierarchical extractions. So first, we will have the several sets abstractions. In their paper, they have 3 SA layer. And then for every SA layer, they extract multiple radius. So let's discuss more detail. For every SA layer here, they extract multiple radius. For example, the first radius is 0.1, the second radius is 0.2, and 0.4 for the third radius. And for every radius here, we set the different maximum k neighbors that we sample. And because we have the different radius, of course, we will also have the different k neighbors that we limit to sample, right? And from different radius here, we have a multiple scale. Let's say here, the first radius is just this small radius. And then the second radius, we consider another larger radius. And the third one is larger, like this one. And then in each radius here, we do the grouping by subtracting the neighbors to the centroid, and followed by PointNet layer that's fusing this into single point feature space. So again, I draw here this fused to this fused to this. So that's it. For every single SA layer, they extract multiple scales of features. And then instead of only using the single SA layer, they use 3 SA layers. But in this figure, they just draw 2 SA layers just for simplification. So here in the first SA layer, they sample into this number of 512. And then in the second SA layer, they sample into this number of centroid. And in the last SA layer, they only sample 1 centroid. And as we can see that as we go deeper here, we can think that every point here, they have a larger coverage. Let's see. So this single point, it covers this, right? If we see the outermost of this radius, let's see here correspond to around this point, and this point around probably around this positions, and this position they consider the neighbors like this, right? These neighbors, and then another outer point here that is captured by this. Oh, sorry, this one. This will be around here, and again we will have here, and so on and so forth. So for every single point here, it will have larger coverage around this region, which is larger than if we have the previous set abstraction here, right? Let me redraw for cleaner visualization. This single point cover this region, and this single point will cover like this region, larger region. And this is comparable with the CNN, convolutional neural network. As we go deeper, its kernel, it's the filter kernels, we also have the larger coverage, or we call this as a receptive field. Yeah, this is similar. And then see the pattern here. As we go deeper, we sample only fewer centroids, right? And fewer centroid, it will capture a larger coverage. So that's why we need higher embedding dimension, because naturally if we represent larger coverage, we need more space to represent this feature learning. So this is how the PointNet ++ capture the hierarchical extractions. And let's see the applications in the classifications, and later we see the another applications in the segmentation network. For the classifications, I think this is pretty straightforward. So the target for the classification network is we want to have the single vector in the end of this network to have a k embedding dimensions, which corresponding to the k is the number of class, the number of category in the dataset, right? And for every node in the k here just correspond to single probability of certain class. And actually in the end of days, we already have the single vector here. So to get this, we basically just apply some MLP to map from this embedding dimensions to another embedding dimension, and again into this 256 dimension, and finally we map to this k dimensions, and this k dimensions just represent the probability of each category in the dataset. That's it for the classification network. And then for the semantic segmentation network, so the target of the segmentation network is we have to obtain the number of original points. Let's say the original point is 2048 here. We also want that the end of this network also have the exact same number here, and then with the embedding dimension of k, where k is the number of the class. So we want to classify for every point belongs to which class. That's it. And because of the hierarchical extraction here, as we go deeper, we have a viewer centroid. We need to restore back. We need to do the upsampling. And to do the upsampling, in this PointNet ++, they do interpolations. So this is the number of centroid we sample in the last layer here. Again, we only show the 2 SA layer, but actually their paper they have 3 SA layer. Here is correspond to this number. And then we want to interpolate from this number of point features to this number of point features. To do the interpolations, I think it's also straightforward. Let's see, let's consider this particular point, or I just use this one. This particular point, this correspond to around this position, and PointNet ++ they consider 3 nearest neighbors. In this case, is this 3, 1, 2, 3, and they just do interpolations from these features, because yeah, this centroid we have the original coordinate, right? And this is also the original coordinate, and we take the corresponding point features in the previous layer here and do the interpolations by computing the distance between this centroid to the neighbors. If we have the closer neighbors, we will have the higher weight. So it's just inversely proportional to the distance. That's basically just how interpolation works. And then after we interpolate, we have days from this number into this number. We apply stack of MLP to fuse the features. And also when we do fusing here, we also consider the skip connection. Just think of UNet here, UNet, but in this figure we just throw in the different direction, UNet like this, UNet, and this correspond to, let me delete, this correspond to this. We have the same dimension, right? This and this. Just do concatenations. We have the same points number, and this is the embedding dimension. Concatenate along these dimensions and do the fusing. This is after the interpolations, and we concatenate, and then we fuse by using this unit PointNet, which is stack of MLP, and this is the fused feature here. And again, we do the another interpolation. Let's see, from this number, we interpolate into this original point, right? This corresponds to this number with the embedding dimension E here. And then finally, we map this embedding dimension into K. N is just basically this number. And finally, we can classify for every point here. We maximize the corresponding KTH semantic label in the dataset. Yeah, I think that's it for the segmentation network. And let's see, the next is the experimental result. Here we have a segmentation result from the indoor scene dataset from PointNet and also PointNet++, and this is the corresponding ground truth here. And as we can see here that the PointNet missed some segmentation around this region. This corresponds to the door and also the desk, and the PointNet++ can segment this. And also here we have this is correctly segmented. And also here, this is very obvious. This is correctly segmented, and this is wrong segmentation. That's it for this video sections. In this video sections, we already discussed the backbone of the point cloud, which is PointNet++, is the further development of PointNet. And for the newer backbones, actually, if later you read some newer papers, they basically just build on top of this concept, which is the stack of MLP, or they will use another extractor, and they will consider the neighbors, and they also consider the hierarchical extractions. So I hope by having this understanding about this PointNet and PointNet++, it will give us a strong enough foundations if later we see a newer backbone. Yeah, that's it, and see you in the next video.